What if I told you that some of the most advanced engineering marvels in human history weren't created in our modern era of supercomputers and precision tools, but over 3,000 years ago, with nothing more than bronze, stone, and sheer ingenuity? Picture this, a world where ancient architects designed structures so precise, so resilient, that even today, with all our cutting-edge technology, we can't fully figure out how they did it. These weren't just builders, they were visionaries, masters of their craft, whose secrets have been buried by time but whose legacies still stand, silent and awe-inspiring, waiting to be rediscovered. Take a moment to think about the last time you marveled at a modern skyscraper or a feat of engineering. Now imagine standing in front of a monument built in the Bronze Age, a time when humanity had no blueprints, no cranes, no digital simulations, and realizing that its construction is still a mystery. These forgotten engineers didn't just stack stones, they defied gravity, harnessed natural forces, and created systems that functioned with near magical efficiency. Some of their water channels, for example, flow with such perfect precision that modern hydrologists scratch their heads. Others built walls so tightly fitted that not even a blade of grass can slip between the seams. How? That's the question that haunts researchers to this day. This isn't just a story about the past, it's a humbling reminder of what humans are capable of when creativity and determination collide. These ancient innovators didn't have textbooks or YouTube tutorials. They had observation, trial and error, and an intimate connection to the materials and world around them. And somehow they left behind puzzles that we're still trying to solve. So join me as we step into their world, peeling back the layers of time to uncover the brilliance of the Bronze Age's greatest minds. By the end of this journey, you'll see history and human potential in a whole new light. The dawn of the Bronze Age wasn't just a shift in materials, it was a revolution in human potential. Imagine a world where the discovery of mixing copper and tin didn't just give us stronger tools, but unlocked entirely new ways of thinking. For the first time, societies could dream bigger, build taller, and engineer solutions to problems that once seemed insurmountable. This wasn't just about better axes or sharper swords. It was the birth of precision, the moment humanity learned to manipulate metal with such skill that it transformed every aspect of life. Take the humble nail, for example. Before bronze, structures were held together by ropes, notches, or sheer weight. But with the ability to cast and shape metal, builders could fasten beams securely, creating sturdier homes, grander temples, and eventually the first true cities. And it wasn't just about construction. Bronze plows turned tough soil into fertile fields, while metal-edged wheels made trade and travel easier than ever. Suddenly, the impossible became possible. Yet the real marvel wasn't the metal itself, but the minds behind it. These early engineers didn't just copy what came before. They experimented, innovated, and pushed boundaries. They discovered that adding a pinch of arsenic to bronze made it harder, or that heating and cooling metal in just the right way could prevent cracking. These weren't random accidents, they were the first steps toward real material science, laid down millennia before the word engineering even existed. And then there's the infrastructure. From the winding irrigation canals of Mesopotamia to the paved roads of the Indus Valley, Bronze Age societies didn't just build objects, they built systems. Networks of waterways that turned deserts into breadbaskets, or harbors designed to withstand storms and tides. These weren't haphazard projects, they were calculated, deliberate feats of planning and coordination, proof that these ancient innovators understood their world in ways we're still unraveling today. What's truly astonishing is how little they had to work with. No calculus, no steel, no power tools, just observation, trial and error, and an unwavering drive to improve. That's the legacy of the Bronze Age, not just the artifacts left behind, but the bold spirit of problem-solving that still inspires us today. Now let's talk about the stones, the ones that make archaeologists and engineers alike stop in their tracks. Scattered across the globe, from the windswept plains of Salisbury to the scorching deserts of Egypt, stand monuments so massive, so meticulously placed, that they seem to whisper secrets we've yet to fully decipher. These aren't just piles of rock, they're puzzles carved in granite, each one a testament to a level of precision that shouldn't have been possible thousands of years ago. Consider Stonehenge. Those iconic standing stones, some weighing over 25 tons, were hauled from quarries nearly 150 miles away. Forget wheels or draft animals, the technology simply didn't exist yet. So how did they do it? One theory suggests they used a combination of sledges, rollers, and sheer manpower, lubricating the path with water to reduce friction. Others propose they might have leveraged the landscape itself, waiting for winter ice to slide the stones along frozen tracks. But here's the kicker: even if we accept these methods, the real mystery lies in the alignment. The stones are positioned to capture the solstice sun with pinpoint accuracy, a feat requiring not just brute strength, but an intimate understanding of astronomy passed down through generations. Then there's the Great Pyramid of Giza, a structure so precise that its sides align with the cardinal points of the compass with an error margin of just a fraction of a degree. Modern engineers using GPS still marvel at this. The builders didn't just stack blocks, they calculated. They understood geometry, leveling techniques, and perhaps even used the stars as their blueprint. Some researchers believe they employed a system of water-filled trenches to ensure a level foundation, while others speculate about shadow casting tools to track the sun's path. But the truth, we're still piecing it together, and let's not forget the lesser-known marvels like the dolmens of Korea or the temples of Malta. These structures share a common thread: stones weighing dozens of tons, fitted together without mortar, yet so tightly you can't slip a sheet of paper between them. The precision suggests a knowledge of stone cutting and joining techniques that rival modern craftsmanship. Were they using primitive proto-saws with sand as an abrasive? Did they have access to lost tools or techniques that simply vanished from history? What's most striking isn't just the how, but the why. These weren't random acts of construction. The alignments with solstices, equinoxes, and star patterns hint at a deeper purpose: calendars, temples, or even gateways to the divine. The builders didn't just move stone, they moved knowledge, encoding their understanding of the cosmos into the very bones of the earth. Today, as we stare up at these monuments, we're not just looking at ruins. We're looking at the fingerprints of geniuses who worked without textbooks, without calculators, and yet left behind a legacy that still humbles us. Bronze wasn't just a discovery, it was an act of alchemy. When ancient metallurgists first combined copper and tin, they weren't just mixing metals, they were rewriting the rules of what was possible. The genius lies in the ratios: too much tin and the alloy becomes brittle, too little and it lacks strength. Yet somehow these early smiths, working without modern chemistry or precision scales, landed on near-perfect blends, some matching formulas we'd only rediscover millennia later. Take the Nebra sky disk, that breathtaking Bronze Age artifact depicting celestial bodies with uncanny accuracy. The metal itself tells a story. Analysis shows its creators used a copper-tin alloy with just the right balance, around 9% tin, to make it durable yet workable. But here's what's truly baffling. Traces of arsenic in the mix, likely from impure ores, actually improved its quality. Modern experiments prove this accidental contamination, made the bronze harder and more resistant to corrosion. Were these smiths aware of this effect, or did centuries of trial and error lead them to favor ores from specific mines? We may never know. Then there's the casting. The Hittites of Anatolia produced bronze artifacts so thin and intricate they resemble modern pressed metal. How? They likely used clay molds lined with beeswax, a technique called lost wax casting that allowed for astonishing detail. But the real magic happened in the cooling process. By controlling temperature gradients, they prevented cracks and weaknesses that stump even today's artisans. Some scholars believe they may have buried hot castings in ash to slow cooling, a method that only resurfaced in industrial foundries centuries later. And let's not forget the tempering. A Bronze Age sword wasn't just poured and polished, it was transformed. Smiths would hammer the edges while cold, compressing the metal's crystalline structure to make it harder. Then came the annealing, heating and slowly cooling the blade to relieve stress without losing hardness. The result, weapons that could hold an edge through battle after battle, their secrets buried with the smiths who forged them. Perhaps most humbling are the impossible artifacts like the Antikythra Mechanism's bronze gears, with teeth cut so precisely they mesh like clockwork. Or the Chinese ritual vessels cast with interlaced patterns no modern cobbler could replicate without computer-aided design. These weren't just objects, they were masterclasses in material science, proof that the Bronze Age wasn't a stepping stone to better technology. It was a peak we're still struggling to summit. Water was the lifeblood of Bronze Age civilizations, and mastering its flow wasn't just practical, it was an art form. Picture a sprawling city in ancient Crete, where terraced farms flourished in arid hillsides, fed by a labyrinth of underground clay pipes that channeled water with gravity-defying precision. Or the Khanats of Persia, tunnels carved through mountains with nothing but bronze tools and human labor, delivering fresh water across dozens of miles without a single pump. These weren't just ditches dug in the dirt, they were feats of hydraulic engineering so advanced they'd put some modern systems to shame. Take the Minoans of Crete, for example. Their palace at Knossos boasted a drainage system so sophisticated it could handle sudden downpours without flooding, a problem some of our cities still struggle with today. Clay pipes tapered at one end to increase water pressure, while carefully graded slopes ensured waste flowed away from living spaces. But here's what's truly remarkable. These pipes were designed with a self-cleaning feature. The Minoans understood that faster-moving water prevented clogs, so they calculated the exact angles needed to keep everything flowing smoothly. How? Trial and error, observation, and an intuitive grasp of physics that textbooks wouldn't formalize for thousands of years. Then there's the Khanat system, a marvel of ancient Persia that turned deserts into oases. Imagine digging a vertical shaft deep into the earth until you hit groundwater, then tunneling horizontally for miles, all while maintaining a gentle slope to let water trickle downhill without eroding the walls. The math alone is staggering. A slope too steep and the water would rush violently, collapsing the tunnel. Too shallow and it would stagnate. Yet these engineers, using nothing but ropes and plumb bobs, achieved gradients as precise as 1 meter drop per kilometer of tunnel. Even more impressive, they spaced ventilation shafts at exact intervals to prevent toxic gas buildup, a safety measure we'd only rediscover in modern mining. But perhaps the most humbling example comes from the Indus Valley, where entire cities like Mohenjo-Daro were built with standardized, baked brick sewers. Every house connected to a main drain, with manhole covers for maintenance, a level of urban planning unmatched until the Roman era. And unlike later civilizations that relied on slave labor, these systems were clearly designed for public health, with clean water kept separate from waste. It's a reminder that engineering isn't just about brute force. It's about foresight, community, and a deep respect for the natural world. What ties these systems together isn't just ingenuity, it's observation. These ancient engineers didn't have formulas or flow charts. They watched how water moved through cracks in stones, how eddies formed in river bends, and applied those lessons on a grand scale. They turned nature into their blueprint, and in doing so, left behind mysteries we're still unraveling. Like the aqueducts of Petra, carved into cliff faces with such precision that even during droughts, water trickled reliably. Or the terraced rice paddies of ancient China, where every contour of the land was sculpted to hold and distribute water like a living machine. The real question isn't just how they built these systems, it's why we ever stopped seeing the world the way they did. In an age of concrete and steel, we've forgotten the elegance of working with nature rather than against it. These Bronze Age visionaries didn't just move water, they danced with it, and their legacy flows on, whispering secrets to those willing to listen. The seamless stonework of the Bronze Age isn't just impressive, it's borderline inhuman. Walk up to the walls of Mycenae, where massive limestone blocks lock together so perfectly that after 3,000 years, you still can't wedge a razor blade between them. Or step inside Malta's Haga Kim Temple, where curved stone slabs fit like pieces of a jigsaw puzzle, carved with nothing but flint and obsidian. This wasn't just stacking rocks, it was a high-stakes game of architectural Tetris, played without modern tools, without mortar, and somehow without error. So how did they do it? One theory points to a technique called anathyrosis, where builders would carve the edges of each block with a slight concave depression, leaving only the outermost rim perfectly flat. When pressed together, these rims created an airtight seal, while the hollow center reduced friction and made adjustments easier. It's like fitting Lego bricks with microscopic precision, except these bricks weighed several tons and were shaped by hand. But here's the catch: this method requires an insane level of consistency. A single block cut a millimeter too wide would throw off the entire wall. Yet somehow, these masons worked with tolerances that rival modern machine shops. Then there's the mystery of the angles. At Sacsayhuaman in Peru, zigzagging walls feature stones with as many as 12 perfectly interlocking sides. No two blocks are alike, yet each fits its neighbor like a glove. Some researchers suggest they used a system of clay molds pressing soft material against existing stones to create a negative template for the next block. Others believe they employed string and plumb lines to map irregularities. But the truth is, we've never found their tools or blueprints, just the stones themselves, silently mocking our assumptions. And let's talk about the elephant in the quarry. How did they move these behemoths? The trilithons of Baalbek in Lebanon include monoliths weighing over 800 tons, equivalent to 3 blue whales. Even with modern cranes, positioning them would be a nightmare. Yet Bronze Age builders not only transported these giants, they lifted them onto platforms 20 feet high. Some legends speak of levitation or sound waves, but the real answer might be simpler: leverage, sledges, and an army of workers pulling in perfect sync. A recent experiment showed that a team of 40 could move a 1-ton stone nearly 200 feet in an hour using just wooden rollers and ropes. Scale that up, add generations of trial and error, and suddenly, the impossible starts to look plausible. But the most haunting question isn't how, it's why. Why invest centuries perfecting this craft? Maybe the answer lies in the spiritual. At Newgrange in Ireland, a tomb's entrance aligns with the winter solstice sunrise, flooding the chamber with golden light. The builders didn't just want walls, they wanted wonders, structures that bridged earth and sky, mortal and divine. Every seamless joint was a prayer, every balanced stone a covenant with eternity. Today, as lasers scan these walls searching for tool marks, we're not just studying engineering. We're decoding a language written in stone, one flawless connection at a time. Buried beneath the waves for over 2,000 years, the Antikythra Mechanism wasn't just another shipwreck relic. It was a time capsule of genius. When sponge divers first pulled this corroded bronze lump from the Aegean seabed in 1901, no one could have guessed it would rewrite history. After decades of painstaking reconstruction, researchers realized they weren't looking at a simple navigational tool. They were holding the world's first analog computer, a device so advanced it could predict solar eclipses, track Olympic cycles, and map the erratic dance of planets across the sky, all with a system of interlocking gears more intricate than anything Europe would see again until the 14th century. What makes this machine so astonishing isn't just its existence, but its precision. The main gear alone had 223 teeth, each hand cut to mesh perfectly with others no thicker than a coin. To put that in perspective, medieval clockmakers wouldn't achieve similar craftsmanship for another 1,000 years. Even more mind-bending, the mechanism used a differential gear, a component thought to have been invented in the 18th century, to calculate the moon's phases by subtracting one celestial motion from another. This wasn't just technology ahead of its time, it was technology that seemingly skipped entire eras before resurfacing. But here's the real puzzle: who built it? The shipwreck dates to around 60 BCE, but the design hints at origins even earlier, possibly tied to the legendary mathematician Archimedes. Ancient texts describe him creating celestial globes, and one account mentions a device that could model the heavens, eerily similar to the Antikythra Mechanism. Yet no other examples have ever been found. Was this a one-of-a-kind masterpiece, or the last survivor of a lost tradition of mechanical genius? The mechanism's purpose deepens the mystery. Unlike monumental stonework, this wasn't built for kings or gods. Its inscriptions suggest it was an educational tool, meant to demonstrate the harmony of the cosmos. Imagine a philosopher turning its hand crank, watching miniature planets orbit in perfect sync, a portable universe powered by bronze gears. In a world where most believed the heavens were ruled by capricious deities, this machine whispered a radical idea: the universe might follow predictable mechanical laws. Today, as high-resolution scans reveal hidden inscriptions and previously unknown functions, we're left with more questions than answers. How did ancient Greeks grasp gear ratios we'd associate with Renaissance engineering? Why did this knowledge vanish for centuries? The Antikythra Mechanism doesn't just challenge our timeline of technological progress. It forces us to wonder what other marvels were lost to time, and what that says about the untapped potential of human ingenuity. The palaces of Minoan Crete weren't just buildings, they were living machines designed with a sophistication that makes some modern architects blush. Take the sprawling complex of Knossos, where sunlight filtered through carefully positioned light wells, illuminating deep interior spaces without a single electric bulb. But the real magic lay beneath the floors, where clay pipes snaked through walls in a network so advanced it wouldn't look out of place in a 21st century eco-resort. These weren't just drains, they were climate control systems, circulating cool air in summer and channeling rainwater to prevent flooding during winter storms. What's truly staggering is how the Minoans approached earthquakes. Living on an island crisscrossed by fault lines, they didn't just build to withstand tremors, they built to dance with them. Walls were reinforced with wooden beams, acting as shock absorbers that flexed rather than shattered. Columns tapered downward, a counterintuitive design that redistributed seismic energy. Even their famous bull-leaping frescoes might hold a clue. Some scholars suggest the dynamic poses mirror the very movements these structures were engineered to survive. It's as if they encoded their architectural secrets in art, leaving breadcrumbs for future generations to follow. Then there's the matter of scale. The Palace of Malia covered over 75,000 square feet, yet every corridor, every stairwell was designed with human movement in mind. Staircases had shallow treads for ease of climbing, while strategic openings created natural airflow. No stuffy corridors here. And let's talk about those iconic tapered columns, painted vibrant red and black. Beyond their beauty, their shape served a purpose, wider at the top to support heavy ceilings while minimizing material use. It's a principle modern architects call structural efficiency, mastered centuries before the term existed. But perhaps the most humbling detail is the Minoans' understanding of hygiene. While medieval Europeans would later toss waste into streets, Crete's palaces had flushing toilets connected to main sewers. Terracotta bathtubs drained through sophisticated piping, and some rooms even featured adjustable ventilation sliding panels that could direct breezes like ancient air conditioning. Recent excavations revealed something even more startling: sections of pipe lined with a self-cleaning lime-scale deposit, proving the Minoans understood water chemistry well enough to prevent mineral buildup. The question isn't just how they achieved this, it's why we ever lost such knowledge. Unlike later civilizations that prized monumentality, Minoan engineers focused on harmony between structure and landscape, between form and function. Their cities lacked defensive walls, suggesting a rare confidence in both their technology and diplomacy. Walking through these ruins today, you don't just see collapsed walls, you glimpse a philosophy, one that saw buildings not as conquests over nature, but as conversations with it. And that might be their greatest lesson of all. The roads of the Bronze Age weren't just dirt paths, they were feats of engineering so durable, some still lie hidden beneath modern highways, whispering secrets of a time when travel was anything but simple. Picture a world without satellites or surveying tools, where builders carved highways through mountains and marshlands using nothing but intuition and muscle. The sheer scale is staggering. The ancient Hittites alone left behind a network stretching over 600 miles, their stone-paved routes cutting across Anatolia like arteries of empire. But what's truly baffling isn't the distance, it's how these roads outlasted civilizations. Take the amber routes of Europe, where traders moved precious Baltic amber southward to the Mediterranean. These weren't haphazard trails but carefully planned corridors, often elevated on causeways to avoid flooding. Archaeologists have found sections where the roadbed consists of layered logs laid crosswise, a technique that distributed weight like modern corduroy roads, preventing sinking in swampy terrain. Even more impressive, some stretches were lined with crushed limestone, which hardened over time into a near-concrete surface. The Romans would later claim credit for such innovations, but evidence suggests Bronze Age engineers mastered them first. Then there's the mystery of the Indus Valley's street grids. At Mohenjo-Daro, main roads ran straight as arrows for miles, with standardized widths that suggest centralized planning. But here's the twist: beneath the brick paving, engineers installed elaborate drainage channels covered with precisely fitted stone slabs. These weren't just gutters, they were part of an integrated system that kept roads dry during monsoons, a feature many tropical cities still struggle to replicate. How did they calculate gradients without levels or theodolites? One theory points to water-filled trenches used as primitive spirit levels, but no one's found definitive proof. Perhaps the most haunting roads wind through the Andes, where the Quijapac-Ñan highway system connected the Inca Empire, but its origins trace back to far older cultures. Some sections feature retaining walls built with polygonal stones that shift during earthquakes rather than crack. a technique modern engineers call seismic damping. Others climb impossible gradients with staircases carved directly into bedrock, their edges worn smooth by countless sandaled feet. The builders understood something we often forget. Roads aren't just about getting from A to B. They're about harmony, aligning with the land's natural rhythms rather than forcing it into submission. What unites these ancient pathways is a philosophy lost to time: infrastructure as legacy. Today's asphalt crumbles in decades, yet Bronze Age roads endure, not because their materials were superior, but because their builders thought in centuries. They chose routes based on animal migrations, seasonal streams, even star patterns, embedding resilience into every stone. As modern roads buckle under climate change, perhaps it's time to look back at these forgotten engineers who walked the earth lightly but left footprints that never faded. The open sea was the Bronze Age's great highway, a vast, unpredictable frontier that demanded ships as resilient as the people who sailed them. Picture a vessel like the Uluburun, a merchant ship that sank off the coast of Turkey around 3,300 years ago. When divers rediscovered its wreck in the 1980s, they found more than just a time capsule of cargo. They uncovered a masterpiece of maritime engineering. Its hull, built from Lebanese cedar planks stitched together with flexible tenons and pegs, could twist with the waves like a living thing. This wasn't just a boat, it was a symphony of wood and craftsmanship, designed to flex rather than fracture under the ocean's relentless pressure. But the real genius lay in the details. Take the Phoenician ships, their prows carved into horse heads, their sails dyed purple with precious murex ink. These weren't just symbols of status, they were innovations. The Phoenicians understood hydrodynamics centuries before the term existed. Their hulls, tapered at both ends, reduced drag, while keels extended deep into the water for stability. Some vessels even featured a primitive form of ballast, with stones strategically placed to lower the center of gravity. Imagine navigating the Mediterranean's capricious currents without compasses or charts, relying instead on an intimate knowledge of stars, winds, and wave patterns. These sailors didn't just ride the sea, they danced with it. Then there's the mystery of the sewn plank technique. From Scandinavia to the Indian Ocean, cultures independently developed methods of lashing planks with cords made of plant fibers or animal sinew. The result, ships that could be disassembled for repairs or portaged across land, a flexibility modern shipbuilders are only now rediscovering with modular designs. The Bronze Age sailors of Oman took this further, waterproofing their hulls with a paste of fish oil and lime, a recipe so effective it repelled barnacles for decades. What's most astonishing isn't just the engineering, but the ambition. The Uluburun carried 10 tons of cargo copper ingots, glass beads, even ostrich eggs from 7 different civilizations. This wasn't coastal hopping, it was intercontinental trade on a scale we rarely associate with antiquity. These ships connected Egypt to the Aegean, Mesopotamia to the Indus Valley, carrying not just goods but ideas. The very shape of a hull, the weave of a sail, became a language spoken across thousands of miles. And let's not forget the unsung material, bitumen. Mesopotamian shipbuilders coated their vessels with this natural tar, creating a waterproof barrier so durable that some remnants still cling to ancient docks. Recent experiments show it's more effective than modern synthetic sealants in resisting saltwater corrosion. How did they discover this? Trial and error, likely, but also observation, noticing how natural seeps of bitumen preserved reeds and wood along riverbanks. The legacy of these forgotten shipbuilders isn't just in the wrecks we've found, but in the horizons they opened. Their vessels were more than transportation. They were bridges between worlds, carrying not just spices and metals, but the very roots of globalization. Today, as archaeologists piece together their techniques, we're left with a humbling truth. The sea, which we now cross in hours, was once a realm of patience, skill, and reverence, a reminder that sometimes the oldest ways are the most profound. The Pantheon stands in Rome after nearly 2,000 years, its dome still the largest unreinforced concrete structure on Earth, defying earthquakes, wars, and the relentless march of time. What's its secret? A recipe so advanced that modern labs are only now decoding its genius. While we often credit the Romans, the roots of this technology stretch back further, to Bronze Age innovators who first unlocked the alchemy of durable construction. Their concrete wasn't just strong, it was alive, capable of healing its own wounds like living tissue. Take the harbors of the ancient Mediterranean. Built to withstand crashing waves, many still exist today, submerged but intact, while modern counterparts crumble after decades. The magic lies in the mix. Analysis reveals these builders used volcanic ash, a key ingredient that reacts with seawater to form rare minerals. Over time, tiny cracks actually trigger a chemical cascade. Water seeping in combines with residual ash to grow new crystals, welding the gap shut. It's a process so elegant, scientists now call it autogenous healing. Modern engineers have tried replicating it with embedded bacteria or microcapsules, but the ancient version works better, requiring no artificial additives. But here's what's truly baffling: the precision of their ratios. At Pozzuoli near Naples, researchers found concrete piers containing exactly 75% volcanic sand and 25% lime, a balance that optimizes strength and flexibility. How did they arrive at this formula without modern chemistry? Trial and error, certainly, but also an almost poetic attention to nature. The same volcanic regions that threatened their cities also gifted them the perfect building materials. These engineers didn't just exploit resources, they collaborated with them, turning geological chaos into architectural harmony. Then there's the mystery of the additives. Some samples contain animal blood or milk proteins, substances that sound primitive but actually slowed curing, preventing cracks from forming during drying. Others include crushed pottery, which acted like tiny reinforcement bars, distributing stress. The most startling discovery, crystalline structures called stretlingite, formed when local clays reacted with lime, a natural fiberglass that made concrete resistant to saltwater corrosion. These weren't random experiments, they were calculated innovations, each tweak a response to real-world failures and observations. What's humbling isn't just their success, but their philosophy. Unlike today's disposable infrastructure, Bronze Age and Roman builders thought in centuries. They accepted that materials would evolve, that cracks would form, and instead of fighting it, they engineered resilience into the very chemistry of their creations. As modern concrete skyscrapers require costly repairs after mere decades, these ancient structures whisper a challenge. Perhaps durability isn't about defying nature, but learning from it. The recipe wasn't lost, it was waiting for us to rediscover the wisdom in its simplicity. Bronze Age swords weren't just tools of war, they were masterpieces of metallurgy, forged with techniques modern blacksmiths still struggle to replicate. Take the Mycenaean Type B swords, recovered from royal tombs with edges so sharp they could slice through leather armor like parchment. What made these weapons extraordinary wasn't just their lethal elegance, but the science behind them. Bronze, an alloy of copper and tin, could be work-hardened by hammering, creating a blade that bent rather than shattered in combat. This was crucial in an era when broken weapons meant certain death. The secret lay in the precise tin content, around 10%, giving the alloy just enough flexibility to absorb impacts while maintaining a razor edge. Later iron swords, though harder, often proved brittle by comparison, snapping under stress until steel-making techniques evolved centuries later. Then there's the mystery of the casting process. Unlike iron, which requires furnaces reaching extreme temperatures, bronze could be melted in clay crucibles over open fires, but the real genius emerged in the finishing. Artisans would cold hammer the edges, compressing the metal's crystalline structure to triple its hardness. Some blades even show evidence of annealing heated and slowly cooled to relieve internal stresses. The result, weapons that stayed lethal through battle after battle, their resilience unmatched until the rise of medieval Damascus steel. Chariots reveal another layer of innovation. Egyptian designs used bronze axle caps to reduce friction, allowing lighter frames that outpaced heavier opponents. Recent experiments show these caps, when lubricated with animal fat, could spin for miles without overheating. And let's not forget the composite bow, layers of wood, horn, and sinew laminated with fish glue, storing more energy than any solid wooden bow. Fired from a moving chariot, these arrows could pierce armor at 200 paces, a feat that wouldn't be surpassed until the English longbow. Perhaps most fascinating is what these weapons tell us about Bronze Age society. The labor required to produce a single sword, mining ore, smelting, casting, polishing meant weapons were both tools and status symbols passed down generations. Their designs weren't static, they evolved in response to new threats like the antenna-hilted daggers of Central Europe, whose distinctive handles provided better grip in close combat. This wasn't just craftsmanship, it was survival, refined over centuries into an art form. The irony, bronze's very perfection may have delayed the adoption of iron. Why switch to a cruder metal when your weapons already danced on the edge of perfection? It took the collapse of Bronze Age trade networks and the scarcity of tin to force the transition. Even then, iron only surpassed bronze when smiths learned to carburize it into steel, a process that echoed the very alloying principles Bronze Age metallurgists had mastered millennia earlier. Their legacy isn't just in the blades that survived, but in the realization that sometimes the oldest solutions are the most enduring. Standing stones and temple doorways weren't just placed randomly, they were celestial compasses, locked in silent conversation with the cosmos. Consider Newgrange in Ireland, a 5,000-year-old tomb where the winter solstice sunrise pierces a narrow roof box, flooding the inner chamber with golden light for precisely 17 minutes. This wasn't accidental. The builders calculated the angle of the sun's lowest annual arc to the minute, engineering a spectacle that still draws crowds today. But here's what's even more astonishing. They achieved this without written records or precise instruments, relying instead on generations of naked eye observations passed down through oral tradition. Then there's Egypt's Temple of Karnak, where the axis aligns so perfectly with the midwinter sunset that the dying sun's rays once illuminated the innermost sanctuary's statue of Amun-Ra. The precision suggests the architects used a method called merkit, a simple notched palm rib that functioned like an ancient theodolite. By tracking shadows cast over months or even years, they could map solstices and equinoxes with startling accuracy. Modern experiments show that with just a few wooden stakes and string, observers can determine true north within half a degree, proof that sophistication doesn't always require complexity. But the real showstoppers are the lunisolar calendars encoded in monuments like Stonehenge. The arrangement of the sarsen stones doesn't just mark the solstices, it creates a celestial calculator. The 56 Aubrey holes surrounding the structure likely track the moon's 19-year metonic cycle, used to predict eclipses. Imagine the patience required to document these patterns over lifetimes, then translate them into stone. Recent laser scans revealed tool marks suggesting some stones were adjusted by centimeters over centuries, fine-tuning the alignments like a giant astronomical instrument. Venture to Peru's Chanquillo, and you'll find 13 towers stretching across a ridge like a stony comb. From specific vantage points, these pillars frame the sun's rising positions throughout the year, functioning as a solar calendar so precise it could pinpoint dates within 2 to 3 days. The builders even accounted for atmospheric refraction, the bending of sunlight near the horizon, by subtly offsetting some markers. This level of detail implies not just observation, but a conceptual grasp of celestial mechanics that predates Greek astronomy by millennia. What unites these sites is a shared language of light and shadow. The Mnajdra temple in Malta, for instance, uses strategically placed corbels to cast dagger-like beams onto spiral carvings during equinoxes. In Mesopotamia, ziggurats were oriented to Venus's movements, its 8-year cycle reflected in temple tiers. These weren't just buildings, they were cosmograms, three-dimensional maps of the heavens meant to tether earthly life to cosmic order. The deeper question isn't how they built these alignments, but why they mattered so intensely. For Bronze Age cultures, tracking celestial events wasn't abstract science, it was survival. Solstice markers dictated planting seasons, lunar cycles guided maritime trade, and eclipse predictions reinforced priestly authority. By etching these rhythms into stone, they created eternal witnesses to humanity's first dialogue with the universe, a conversation we're still deciphering, one sunbeam at a time. Beneath the rocky plains of Turkey's Cappadocia region lies a labyrinth so vast it could hide entire civilizations. These underground cities, some descending over 18 levels deep, weren't just temporary shelters. They were meticulously planned metropolises, complete with stables, wineries, and even churches, all carved into volcanic rock with nothing more than bronze chisels and relentless determination. The scale alone is staggering. Derinkuyu, the largest discovered so far, could house up to 20,000 people, with ventilation shafts stretching nearly 200 feet to the surface, delivering fresh air to even the deepest chambers. How did ancient engineers achieve this without blueprints or modern tools? The answer lies in a blend of necessity and brilliance. Start with the air supply, a challenge that would stump most modern architects. The builders carved narrow, vertical shafts that exploited natural temperature differences. Cooler surface air would sink into the lower levels, while warmer air from human activity and cooking rose through separate channels, creating a passive airflow system that prevented stagnation. Some shafts doubled as wells, tapping into groundwater while simultaneously ventilating the city. It's a dual-purpose design so efficient, modern passive ventilation systems still draw inspiration from it. Then there's the matter of defense. Circular stone doors weighing up to a ton could be rolled across passageways to seal off sections in case of invasion. But here's the twist, these weren't just barricades. The door's placement at strategic bottlenecks suggests an intimate understanding of urban warfare. Narrow corridors forced attackers into single file, while hidden escape routes allowed defenders to flank them. Even the staircases were weaponized, short, uneven steps that invaders would stumble over in the dark, while residents navigated them effortlessly from memory. Water management was another stroke of genius. Underground rivers were channeled through clay pipes to communal cisterns, with overflow systems preventing flooding. Some chambers featured grooves carved into walls to condense moisture from the air, a primitive but effective form of dehumidification. And unlike surface cities vulnerable to siege, these subterranean strongholds had secret access points to external springs, ensuring a lifeline even during prolonged conflicts. What's most humbling is the collaborative effort behind these cities. Geological surveys reveal that different levels were excavated over centuries, with each generation expanding and refining the work of their ancestors. The soft volcanic rock, or tuff, was easy to carve but required precise reinforcement to prevent collapses. Pillars were left standing at regular intervals, their spacing calculated through trial and error, a testament to structural intuition we'd later formalize as engineering principles. The real mystery isn't just how they built these cities, but why they abandoned them. Climate shifts, resource depletion, or perhaps they simply outgrew the need for hiding. Walking through Derinkuyu's silent passages today, you're left with a haunting realization. These weren't just survival bunkers, they were a blueprint for resilience, proving that even in the darkest depths, humanity has always found a way to thrive. The walls of Troy weren't just barriers, they were psychological warfare carved in stone. Standing at a staggering 30 feet tall with foundations sunk deep into bedrock, these fortifications didn't just repel invaders, they shattered morale. What made them so formidable? Start with the slope. Unlike vertical medieval walls, Troy's defenses angled outward, forcing attackers to climb upward while exposed to a rain of arrows and boiling oil from above. But the real genius lay in the layers. The citadel wasn't one wall but a series of concentric rings, each higher than the last, creating a deadly maze where even if the outer wall fell, defenders could retreat to the next line, turning every breach into a killing zone. Now consider the gates not just entry points but masterpieces of defensive engineering. At Hattusa, capital of the Hittites, the Lion Gate stood guarded by massive stone beasts, their mouths agape in silent roars. But the true threat was invisible. The gate's corridor twisted at sharp angles, breaking the momentum of charging forces and funneling them into narrow spaces where defenders could pick them off one by one. Some gates even featured hidden postern doors, allowing counterattacks to surge unexpectedly from the flanks. These weren't passive structures, they were tactical puzzles designed to outthink as much as outlast. Materials played a surprising role too. The Mycenaeans mixed clay with crushed pottery in their mortar, creating a lightweight yet shock-absorbent binder that could withstand siege engines. At Ugarit in Syria, walls contained pockets of loose rubble, a primitive form of seismic damping that absorbed earthquake tremors without collapsing. And let's not forget the psychological tricks. Jericho's famous walls may have been plastered smooth and white, gleaming in the sun to dazzle approaching armies, while Thebes' fortifications incorporated jagged stone projections to make scaling attempts suicidal. The most haunting lesson of these ancient strongholds, they were built to adapt. Archaeologists at Megiddo found evidence of walls thickened in response to new siege technologies, showing an iterative design process spanning centuries. Unlike static modern fortresses, these were living systems, evolving alongside the threats they faced. From the glacis slopes that diverted battering rams to the hidden sally ports for guerrilla strikes, every element served multiple purposes, proof that Bronze Age engineers didn't just build walls. They wove invisible nets of stone, waiting patiently for history's greatest armies to entangle themselves. The lost wax method used by Bronze Age artisans wasn't just a technique, it was alchemy in motion, transforming humble beeswax into eternal metal. Picture a Shang Dynasty craftsman carving a delicate deer figurine entirely from wax, its antlers thinner than twigs, every muscle and tendon rendered with lifelike precision. This wax original would then be encased in clay, forming a mold so exact that even the texture of the animal's hide was preserved. When heated, the wax melted away, hence lost wax, leaving a cavity into which molten bronze was poured. But here's where the true magic happened. The clay mold shattered to reveal a metal replica, capturing details as fine as individual eyelashes or the weave of a rope belt. Modern jewelers using 3D printers struggle to match this fidelity, yet these artisans achieved it with nothing but fire, patience, and an almost supernatural understanding of their materials. What's even more astonishing is how they scaled this process. The legendary Sanxingdui masks of China, some standing over 4 feet tall and weighing hundreds of pounds, were cast as single pieces, a feat that defies modern metallurgical logic. The secret clay cores, artisans would sculpt the wax model around a hollow clay form, ensuring even wall thickness during pouring to prevent cracks. Some statues even show evidence of preheating the molds to exactly 600 degrees Celsius, a temperature that prevented thermal shock while allowing the bronze to flow into every crevice. How they measured this without thermometers remains one of history's quiet mysteries. Then there's the alloy itself. Shang bronzes contain trace amounts of lead, not by accident but by design. Laboratory tests reveal this addition lowered the melting point, making the metal flow like liquid silk into intricate patterns. But too much lead would weaken the final product, so artisans calibrated their mixes with near-scientific precision. Some vessels even show gradient compositions, thicker sections alloyed for strength, delicate areas blended for fluidity. This wasn't guesswork, it was material science disguised as art. The real head-scratcher comes when examining pieces like the Humuwu Ding, a ritual cauldron weighing over 1,800 pounds. To cast something this massive, artisans likely dug pits near rivers, using natural slopes to channel molten bronze from multiple furnaces simultaneously. Imagine coordinating this dance of fire and metal without written plans or communication, devices just Chinese letter, and shared intuition. A single misstep could mean months of wasted labor, yet surviving pieces show no flaws, no cold shuts where streams of metal failed to merge. Perhaps most haunting are the tools we've never found. No archaeological site has yielded the precise chisels or miniature spatulas needed for such detailed work. Some scholars suggest they used heated bronze needles to draw in wax, while others propose bamboo tools that rotted away. What's clear is that these weren't just craftsmen, they were illusionists conjuring permanence from the most transient of mediums. Their legacy whispers a challenge across millennia. Perfection isn't about the tools you hold, but the vision you refuse to compromise. While bronze dominated the ancient world, the Hittites were quietly unlocking the secrets of a metal that would redefine history: iron. Nestled in the rocky highlands of Anatolia, their blacksmiths produced weapons and tools unlike anything seen before. A dagger found in the ruins of Hattusa, dating back to around 2500 BC, still gleams with a metallic luster after millennia. What's astonishing isn't just its survival, but its composition. Unlike later iron objects prone to rust and brittleness, this blade contains traces of nickel, evidence it was forged from meteoritic iron, a celestial material revered for its otherworldly strength. But the real breakthrough came when the Hittites moved beyond meteorites. Their smiths discovered how to smelt terrestrial iron ore, a process far more complex than bronze making. While copper and tin melt at temperatures achievable in simple pit furnaces, iron demands blistering heat, over 2,700 degrees Fahrenheit, to separate metal from stubborn rock. The Hittites likely used tall, chimney-like furnaces with bellows to stoke the flames, creating an early version of the bloomery process. The result: spongy masses of iron called blooms, which had to be repeatedly hammered while red-hot to purge impurities. It was grueling work, but the payoff was revolutionary. Weapons that bent rather than shattered, held sharper edges, and could be repaired by reforging. Why did this knowledge remain confined to the Hittite Empire for centuries? Geography played a role. Anatolia's mountains hid rich deposits of both iron ore and the hardwood needed for high-temperature smelting. But the Hittites also guarded their techniques fiercely. Treaties from the era explicitly forbade trading ironworking knowledge, and surviving texts describe iron gifts as royal prestige items, sometimes worth 40 times their weight in silver. A single iron bracelet might be exchanged for an entire orchard. This wasn't just metallurgy, it was geopolitical strategy, a monopoly as carefully protected as modern patents. The most tantalizing clues come from the Hittites' own words. A tablet from their capital describes a ritual where iron was washed like a newborn and fed with eagle fat, hinting at sophisticated carburization techniques. By packing iron in charcoal during heating, they may have accidentally stumbled onto steel making, infusing the metal with carbon to enhance hardness. Recent spectrographic analysis of a Hittite axe head revealed carbon concentrations of 0.5%, nearly identical to modern low-carbon steel. Yet for all their advances, the Hittites never fully abandoned bronze. Their iron artifacts remained rare, reserved for elites or ceremonial use. Some scholars argue this wasn't due to technical limitations, but cultural preference. Bronze was predictable, its properties honed over generations. Iron, though stronger, was temperamental, prone to catastrophic failure if overheated or cooled incorrectly. In a world without thermometers or metallurgical handbooks, mastering iron required not just skill, but a kind of alchemical intuition. The Hittite Empire's collapse around 1200 BC scattered these ironworkers across the Mediterranean, their secrets seeping into neighboring cultures. Within centuries, iron would eclipse bronze, but its rise wasn't inevitable. It began with a handful of artisans who looked at ordinary rocks and saw the bones of the future, their innovations hidden in plain sight, not in grand monuments, but in the quiet gleam of a well-forged blade. Walking through the ruins of Mohenjo-Daro, one detail stops you: cold terracotta pipes protruding from brick walls, a network of drains running beneath streets and into homes. This wasn't just plumbing, it was a hydraulic revolution. The Harappans of the Indus Valley didn't just invent the flush toilet, they engineered an entire ecosystem of water, one where every drop had a purpose. Their cities, built over 4,000 years ago, boasted sewage systems so advanced that medieval Europe would regress to dumping waste into streets for centuries to come. Start with the toilets themselves. Unlike later civilizations that treated sanitation as an afterthought, Harappan homes featured raised brick latrines connected to closed drains. Waste didn't pile up, it flowed through gravity-fed channels lined with precisely fitted bricks, their slopes calculated to prevent clogging. Some residences even had vertical chutes directing sewage to street-level drains, a design echoing modern high-rise plumbing. But here's what's truly remarkable: these weren't luxury features. Even modest neighborhoods had access, suggesting a societal commitment to public health unheard of in the ancient world. Then there's the water supply. Great Bath at Mohenjo-Daro, a monumental pool lined with bitumen to prevent leaks, wasn't just for ritual, it was part of a city-wide hydraulic network. Wells strategically placed every few blocks, tapped into groundwater using cylindrical bricks that resisted collapse. Recent studies show their builders understood aquifer mechanics, choosing locations where water tables replenished quickly. And unlike Roman aqueducts that required massive elevation drops, Harappan systems worked with subtle gradients, some as slight as 2 centimeters per meter, a precision that would challenge modern engineers without laser levels. The real magic, though, lay beneath the streets. Covered drains ran parallel to main thoroughfares, their trapezoidal cross-sections engineered to optimize flow. At intersections, sediment traps filtered debris, while corbelled arches distributed weight to prevent collapses. Maintenance was baked into the design. Access holes at regular intervals allowed cleaning, and some channels even had grooves for wooden screens to strain larger particles. This wasn't just infrastructure, it was a living system designed to adapt and endure. What's most humbling is the scale of their foresight. During monsoons, excess rainwater was channeled into reservoirs, easing flood risks while storing water for dry seasons. Houses had soaking pits for grey water filtration, filled with sand and charcoal, a primitive but effective purification method. Even the bricks tell a story. Standardized ratios 4:2:1 meant every component fit seamlessly, whether in a palace or a sewer. The lingering question isn't just how they built these systems, but why the knowledge vanished. When later cultures like the Vedic peoples migrated into the region, they abandoned urban planning for centuries. Some scholars suggest climate shifts disrupted the delicate balance Harappans had mastered, while others point to a cultural shift away from centralized authority. Whatever the reason, walking these ruins today feels like stumbling upon a blueprint for the future, one where clean water and sanitation weren't privileges, but the foundation of civilization itself. The year 1200 BC marked the beginning of the end for the Bronze Age's greatest civilizations. From the Hittites in Anatolia to the Mycenaeans in Greece, palace after palace burned, trade routes crumbled, and entire cities were abandoned. The collapse was so sudden, so complete, that historians still debate its causes. Was it the mysterious sea peoples invading by boat, a catastrophic drought, or perhaps a perfect storm of interconnected failures? But beneath the ruins lies an even greater tragedy, the loss of knowledge. These weren't just cities falling, they were libraries burning, generations of engineering wisdom vanishing into the smoke. Take the Hittites, masters of ironworking who guarded their metallurgical secrets like state treasures. When their capital Hattusa was torched, the flames didn't just consume buildings, they erased techniques for carburizing iron that wouldn't resurface for centuries. Or consider the Mycenaean drainage systems, so advanced they rivaled Rome's, yet forgotten until modern archaeologists unearthed their remains. The collapse didn't just topple kingdoms, it severed the thread of innovation, plunging the Mediterranean into a dark age where even writing disappeared for generations. Climate change likely played a role. Tree rings from the era show prolonged droughts, while sediment cores reveal sudden drops in agricultural productivity. Imagine entire regions starving, their engineers too focused on survival to pass down knowledge. But there's another layer: interdependency. Bronze Age civilizations relied on sprawling trade networks for tin, the crucial ingredient in bronze. When those supply chains snapped, metalworking ground to a halt. Suddenly, the artisans who once cast flawless statues were reduced to recycling old scrap, their skills fading with each makeshift repair. Yet some mysteries defy easy explanation. Why did survivors abandon advanced water systems for primitive wells? Why revert to simple pit houses when their ancestors had built earthquake-resistant palaces? The answer may lie in trauma. Societies under stress often retreat to what's familiar, discarding complexity for survival. The engineers who remained likely turned their talents to immediate needs, fortifications over temples, subsistence over innovation. The most haunting evidence comes from Cyprus, where archaeologists found kilns once used for high-temperature bronze casting repurposed for basic pottery. It's a poignant symbol of decline, the same hands that shaped precision gears now making crude bowls. But here's what's remarkable: fragments of knowledge survived. The Phoenicians, rising from the ashes, preserved shipbuilding techniques that would later circumnavigate Africa. And in Anatolia, scattered blacksmiths kept ironworking alive, their embers waiting to reignite the Iron Age. The collapse wasn't an ending. It was a bottleneck compressing centuries of progress into scattered fragments. When civilizations finally re-emerged, they didn't start from scratch. They pieced together what remained, blending old wisdom with new necessity. The lesson isn't just about fragility, but resilience, how even in collapse, the seeds of rebirth endure. The Pythagorean theorem may carry a Greek name, but its roots dig far deeper into the Bronze Age, where anonymous mathematicians were already whispering its truths through stone and string. Take the ancient Egyptian rope stretchers, surveyors who used knotted cords to measure land after Nile floods. By creating triangles with sides in precise 3-4-5 ratios, they could guarantee perfect right angles, a practical application of the theorem millennia before Pythagoras was born. But this wasn't just about measurement. The precision of pyramid bases, some deviating less than 1% from perfect squares, reveals an intuitive grasp of geometry that textbooks wouldn't formalize for centuries. Beyond Egypt, a Babylonian clay tablet known as Plimpton 322 tells an even older story. Dating to 1800 BC, its cuneiform markings catalog Pythagorean triples, sets of whole numbers that satisfy the theorem, like 5, 12, 13. What's astonishing isn't just their existence, but their complexity. Some triples on the tablet involve numbers so large, historians believe the Babylonians must have had an algorithmic method to generate them. This wasn't just counting crops or tallying trade goods. It was abstract mathematics for its own sake, a glimpse into minds that saw numbers as a language for describing the universe. Then there are the patterns woven into everyday objects. The spirals on Minoan pottery follow logarithmic curves identical to those seen in galaxies and seashells. Celtic torques twist according to the golden ratio, while Indus Valley seals display symmetries requiring advanced partitioning of circles. These artisans weren't just decorating, they were encoding mathematical principles into art, passing down knowledge through visual rhythms rather than written formulas. Perhaps the most humbling realization comes from their tools. Without protractors, the builders of Stonehenge divided the circle into 56 equal Aubrey holes, a number divisible by multiple factors, allowing for solar and lunar alignments. Without calculators, they estimated pi well enough to construct rings with near-perfect circumferences. Their technology might have been nothing more than pegs and ropes, but their understanding transformed these simple tools into instruments of celestial precision. The true genius of Bronze Age mathematics lies in its duality. It was both sacred and practical. The same geometric principles that aligned temples with solstices also strengthened granary walls. The arithmetic that tracked Venus's cycles equally balanced merchant ledgers. These weren't separate disciplines, but facets of a unified world, where numbers bridged earth and sky, commerce and cosmos. As modern scientists rediscover concepts like fractal geometry in ancient designs, we're forced to wonder, did they stumble upon these truths by accident, or did they see layers of reality we're only beginning to uncover? Bronze Age trade routes weren't just highways for spices and metals, they were the original internet, transmitting engineering breakthroughs faster than a galloping caravan. Picture a tin merchant from Anatolia haggling in a Mesopotamian marketplace, casually mentioning how his people fortified walls with timber braces, or a Cretan sailor demonstrating the self-cleaning slant of his clay pipes to dockworkers in Egypt. These weren't mere transactions, they were masterclasses in innovation, where every exchanged artifact carried hidden knowledge in its design. The evidence is etched into the archaeological record. Take the spread of the Cyclopean masonry technique, massive, interlocking stones fitted without mortar, from Mycenae to the Hittite capital of Hattusa. The resemblance isn't coincidental. Mycenaean traders, drawn by Anatolia's silver mines, likely shared construction secrets along with their olive oil cargo. Similarly, the sudden appearance of corbelled arches in both Scottish Brochs and Sardinian Nurag hints at maritime networks stretching across the Mediterranean, where shipbuilders doubled as inadvertent teachers. But trade's greatest gift might have been standardization. When merchants from the Indus Valley began exporting precision-made brick weights to Mesopotamia, they didn't just sell products, they introduced a system. Soon, Babylonian builders adopted identical brick ratios 4 to 2 to 1, enabling seamless collaboration across linguistic barriers. The Uluburun shipwreck off Turkey tells the same story. Its cargo included copper ingots shaped like ox hides, each matching standardized weights used from Cyprus to Sicily. This uniformity didn't just simplify commerce. It created a shared engineering language where a mold in Crete could cast a tool usable in Spain. Cultural exchange played an equally vital role. When Egyptian envoys gifted gold-plated chariots to Mitanni rulers, they weren't just displaying wealth, they were transferring technology. The Mitanni quickly reverse-engineered the design, adding their own innovations like spoked wheels, which then spread to the Hittites and beyond. Likewise, the Phoenicians' famed purple dye required complex vats and piping systems, knowledge that traveled with every amphora shipped to Greece or Carthage. Perhaps the most profound exchanges happened in metallurgy. Tin from Afghanistan's Badakhshan mines alloyed with Cypriot copper to create bronze that fueled entire civilizations. Along these routes, smiths compared notes. Armenian craftsmen shared arsenic hardening techniques, while Iberian miners taught tin purification methods. By the time this knowledge reached Britain, local tribes were producing socketed axes so advanced they became a de facto currency across Europe. The lesson written in these ancient trade ledgers is clear: innovation thrives on connection. From the lapis lazuli threading through Mesopotamian ziggurats to the Baltic amber adorning Mycenaean tombs, every traded object carried more than material value. It held the potential to reshape worlds. The Bronze Age's true monument wasn't any single wall or weapon, but this invisible web of shared genius spun across continents by merchants, migrants, and curious minds. Buried beneath layers of time and tradition, the fingerprints of Bronze Age women still cling to the tools and technologies that shaped civilizations. While ancient texts often glorify kings and warriors, archaeology tells a different story, one where women weren't just bystanders, but master craftswomen, metallurgists, and even architects. Take the burial sites at Alaka Höyük in Turkey, where women were interred with finely crafted bronze mirrors and intricate weaving tools, their graves positioned with the same reverence as those of male warriors. These weren't mere domestic items. The mirrors required advanced metal polishing techniques, and the looms featured tension systems so precise they rivaled later medieval designs. Then there's the pottery. In Minoan, Crete, fingerprints preserved on ceramic vessels reveal something startling: nearly half were shaped by women's hands. But these weren't just simple bowls. Some jars, like the ones found at Knossos, feature spouts engineered for controlled pouring, their interiors coated with resin to prevent leaks. Others display intricate mathematical patterns, early examples of geometric coding that may have doubled as measurement guides. The same hands that shaped these vessels likely contributed to the palace's famed drainage systems, where hydraulic principles were applied centuries before Archimedes formalized them. Metalworking tells an even more compelling tale. At the Bronze Age site of Wilburton in England, grave goods include delicate bronze filigree jewelry alongside chisels and anvils, buried with women of high status. Microscopic wear patterns on these tools match those found on ceremonial weapons and armor, suggesting these women didn't just adorn elites, they crafted their regalia. Across Europe, similar burials reveal women buried with metalworking kits, their bones often stained with traces of arsenic, a byproduct of bronze smelting. Far from being confined to domestic spheres, these women were likely the alchemists of their age, experimenting with alloys and temperatures to perfect their craft. Perhaps the most striking evidence comes from textiles, a domain often dismissed as women's work, yet one that demanded engineering genius. The linen wrappings of Egyptian mummies, some woven with 200 threads per inch, required looms with complex pulley systems and tension devices. In Central Europe, Hallstatt culture women developed a method to weave bronze wire into fabric, creating garments that shimmered like liquid metal. These weren't just crafts, they were feats of material science, requiring an intimate understanding of tensile strength and structural integrity. The real tragedy isn't just that these women's contributions were erased, it's how thoroughly we've underestimated the interconnectedness of their work. The same spatial reasoning needed to warp a loom may have informed the layout of megalithic monuments. The precision honed in jewelry making could have translated to the calibration of water clocks. When we dismiss domestic arts as separate from high engineering, we miss the truth. Innovation doesn't respect artificial categories. The Bronze Age women who calculated dye ratios, balanced spindle walls, or tempered metal were working with the same principles that built cities, just on a different scale. Their legacy lingers in subtle clues. The spiral motifs on Minoan pottery mirror the curves of labyrinthine palace corridors. The knotwork patterns woven into Celtic fabrics echo the joinery techniques of timber fortresses. Even the rhythmic pounding of grain in mortars may have inspired the pulsing cadence of bronze casting hammers. These women didn't just participate in the technological revolution of their time. They helped define it, one stitch, one casting, one calculated pour at a time. The question isn't whether women shaped Bronze Age engineering, but why we ever stopped seeing their hands in the work. The towering ziggurats of Mesopotamia weren't just architectural marvels, they were stairways to the gods, each tier a symbolic ascent toward the divine. Built with millions of baked bricks, these stepped pyramids didn't merely elevate temples physically, they encoded an entire cosmology. The 7 levels of Babylon's Etemenanki mirrored the 7 known celestial spheres, while the orientation of their staircases aligned with Venus's cyclical appearances. This wasn't accidental geometry, it was theology written in clay and limestone, a testament to how Bronze Age engineers saw no divide between the spiritual and the structural. Consider the Great Pyramid of Giza's interior shafts, long dismissed as ventilation channels until astronomers realized they pinpointed specific stars, Thuban in the northern sky and Orion's belt, celestial markers tied to the pharaoh's journey to the afterlife. The precision wasn't just about engineering prowess, it reflected a belief that the pharaoh's soul would navigate these stars. Even the pyramid's base perimeter, divided by twice its height, yields pi to 4 decimal places, a mathematical hymn to cosmic order. Across the Aegean, the labyrinthine palaces of Minoan Crete held their own secrets. The double-axe symbols carved into their pillars weren't mere decoration. Known as labries, these motifs represented a goddess's power, while the palace's winding corridors mirrored the mythological labyrinth of King Minos. The very act of navigating these spaces became a ritual where every turn echoed the cycles of life and death. Even the columns, painted red and tapered downward, defied structural logic until scholars realized they mirrored sacred trees, rooted in the heavens and branching earthward. In Britain, Stonehenge's bluestones tell a geological story with spiritual undertones. Transported over 150 miles from Wales' Preseli Hills, these stones weren't chosen for practicality, but for their perceived connection to ancestral land. Geological analysis reveals they were quarried near sacred springs, suggesting their journey to Salisbury Plain was a pilgrimage in stone. The arrangement, marking solstices and eclipses, transformed the monument into a celestial calendar, but also a bridge between the living and the dead, as cremated remains found on-site confirm. The Indus Valley cities hid symbolism in urban planning. Mohenjo-Daro's Great Bath, with its precise dimensions and watertight bitumen lining, wasn't just a public utility. Its proportions matched Vedic altars described millennia later, hinting at an early ritual purification space. The city's grid layout, with streets aligned to cardinal directions, didn't just aid traffic flow, it mirrored the cosmic order, turning the entire settlement into a mandala of harmony. What unites these structures is intentionality. The corbelled arches of Mycenaean tombs, shaped like beehives, symbolize the womb of the earth goddess. The zigzag walls of Peru's Chavin de Huanta, engineered to amplify ritual chants, blurred the line between architecture and sacred instrument. Even defensive walls carried meaning. Troy's sloping ramparts weren't just tactical, their gleaming white plaster mirrored the mythical walls of destiny described in Hittite texts. The genius of Bronze Age engineers lay in their dual vision. A water channel wasn't just a conduit for liquid, but a metaphor for the flow of time. A temple's pillars didn't merely support roofs, they connected earth to sky. In an age before blueprints, these builders worked from a different kind of plan, one where every measurement, every angle whispered secrets of the universe. To study their work isn't just to analyze techniques, but to decode a lost language of stone and symbol, where function and faith were forged together like copper and tin. The arches that support modern stadiums and bridges owe their existence to a simple yet revolutionary idea born in the Bronze Age: the corbelled vault. Ancient builders in Mycenae stacked stones in ever closer rings until they met at the top, creating structures that distributed weight so efficiently, their tombs still stand intact after 3,000 years. Today's engineers use the same principle in concrete domes and suspension bridges, proving that sometimes the oldest solutions are the most enduring. Even the Roman aqueducts, often credited as engineering marvels, were refinements of earlier Bronze Age water channels like those in Knossos, where tapered clay pipes optimized flow rates using gravity alone, a concept now foundational to modern municipal water systems. Look closely at skyscraper construction, and you'll spot another Bronze Age legacy: modular design. The Indus Valley's standardized brick ratios 4:2:1 allowed entire cities to rise with interchangeable parts, a philosophy mirrored in today's prefabricated steel frames. Meanwhile, the seismic-resistant techniques of Minoan Crete, flexible wooden reinforcements and downward tapering columns, are now encoded into earthquake-proof high rises from Tokyo to San Francisco. It's as if these ancient engineers left blueprints we're still following, their trial and error wisdom hardened into codes and regulations. Perhaps the most surprising modern parallel lies in sustainable design. Bronze Age qanats, those mile-long underground tunnels that brought water to Persian deserts, functioned as passive coolers, their buried channels naturally chilling water through Earth's insulation. Contemporary architects are reviving this idea with geothermal cooling systems, while wastewater solutions inspired by Mohenjo-Daro's separated drainage networks now appear in eco-cities. Even the humble wind catcher, a ventilation tower perfected by Bronze Age Mesopotamians, has been reimagined in Dubai's energy-efficient towers, proving that ancient climate control can outpace air conditioning. The connection extends to material science too. Researchers studying Hittite iron alloys recently discovered nanostructures similar to those in modern high-strength steel, hinting at lost heat treatment methods. Meanwhile, the self-healing concrete of Roman harbors, derived from volcanic ash mixes first developed by Bronze Age builders, is now being replicated to repair crumbling modern infrastructure. There's poetic justice in using a 3,000-year-old recipe to fix problems created by our own shortcuts. But the deepest influence isn't just technical, it's philosophical. Bronze Age engineers worked with nature rather than against it, aligning roads with animal migrations and shaping buildings to celestial patterns. Today's biomimicry movement, where solar panels mimic leaf structures and turbines copy whale fins, echoes this same reverence for natural design. In an era of climate crisis, their greatest lesson might be humility. That true innovation doesn't always mean inventing anew, but remembering what we've forgotten. From the gears of the Antikythra Mechanism to the lunar calendars etched into standing stones, these ancient minds mapped a path we're still walking, one where engineering isn't just about moving mountains, but listening to them. Even after centuries of study, the engineers of the Bronze Age still guard their most astonishing secrets. We've reverse-engineered their concrete, mapped their trade routes, and marveled at their celestial alignments, yet some of their achievements remain stubbornly out of reach. Take the vitrified forts of Scotland, where massive stone walls were fused together by heat so intense it turned rock into glass. Modern attempts to replicate this process require temperatures exceeding 2,000 degrees Fahrenheit, yet there's no evidence the builders used furnaces or accelerants. Did they harness natural phenomena like lightning strikes, or was this the result of some lost pyrotechnic technique? The stones won't say. Then there's the enigma of precision. The drill cores extracted from Egypt's pyramids reveal granite blocks drilled with near-perfect circular holes, their symmetry rivaling modern machine tools. The grooves suggest a drilling rate of 1 millimeter per minute, a feat that would require diamond-tipped bits today, yet no trace of such advanced tools has ever been found. Some researchers propose copper drills fed with abrasive quartz sand, but experimental recreations struggle to match the smoothness of the originals. Were these artisans using a forgotten method of ultrasonic vibration or water jet cutting? Or did they possess a patience so profound that weeks of meticulous labor could produce what our machines achieve in minutes? The gaps in our knowledge grow even wider when we confront their logistical miracles. How did the builders of Baalbek's trilithon transport and lift 800-ton stones, twice the weight of anything modern cranes handle routinely, without leaving behind so much as a scratch mark or tool fragment? Contemporary theories involving earthen ramps and lever systems strain under scrutiny when applied to such massive blocks. Even more perplexing are the polygonal walls of Sacsayhuaman, where stones with up to 36 angles fit together like a three-dimensional jigsaw puzzle. Modern engineers using laser scanning and 3D software struggle to replicate the precision of these dry stone joints, yet the builders achieved it with nothing more than bronze chisels and stone hammers. Perhaps the most tantalizing mysteries lie in their material science. The Damascus steel of later centuries owes its legendary properties to trace elements like vanadium, but Bronze Age smiths in Anatolia were producing similarly superior iron alloys millennia earlier. Metallurgical analysis of a Hittite dagger revealed a nanocrystalline structure that defies conventional forging methods. Did they discover a way to manipulate metal at the atomic level through ritualized heating and cooling cycles? Or were they simply more attuned to the secrets hidden within their ores, recognizing qualities our instruments can barely detect? Underwater ruins add another layer of intrigue. Off the coast of Japan, the Yonaguni Monument's terraced formations exhibit right angles and staircases that seem unmistakably artificial. yet they're submerged under 120 feet of water, a depth suggesting construction during the last ice age. If human hands shaped these structures, they would rewrite the timeline of engineering prowess entirely. Similar debates surround Cuba's underwater megaliths and India's Gulf of Combat City, where sonar images reveal geometric patterns far beneath the waves. What's both humbling and exhilarating is how much we might still uncover. Less than 5% of known Bronze Age sites have been excavated, and new technologies like ground-penetrating radar and AI-assisted artifact analysis are revealing hidden chambers and lost cities every year. A single discovery, a buried workshop, a preserved tool cache, an untouched engineer's tomb could unlock the missing pieces of this ancient puzzle. Until then, we're left with the quiet certainty that our ancestors were far more than primitive craftsmen. They were innovators whose full brilliance still lies just beyond our grasp, whispering to us through the stones they left behind. The forgotten engineers of the Bronze Age weren't just builders, they were alchemists of stone, metal, and water, transforming raw materials into feats that still leave us breathless. Their work wasn't just functional, it was poetic, blending precision with purpose in ways we're only beginning to decode. Think about it. These were people who mapped the heavens with nothing but shadows and string, who turned volcanic ash into self-healing concrete, who carved cities beneath the earth with nothing more than bronze chisels and patience. Their genius wasn't just in what they made, but in how they saw the world, a place where every material, every slope of land, every movement of the stars held secrets waiting to be harnessed. What's most humbling is realizing how much we've lost, not just their techniques, but their philosophy. They didn't conquer nature, they collaborated with it. The Minoans built palaces that danced with earthquakes. The Indus Valley engineers designed streets that breathed with monsoons, and the builders of Stonehenge calibrated their stones to the slow heartbeat of celestial cycles. Today, as we grapple with crumbling infrastructure and climate crises, their work whispers a challenge. Maybe progress isn't always about inventing something new, but rediscovering the wisdom buried in ancient stones. The true legacy of these visionaries isn't just in the monuments they left behind, but in the questions they force us to ask. How did they calculate the acoustics of underground temples without sound waves? Why did their bronze alloys outperform early iron? Each unanswered riddle is a reminder that human ingenuity has no expiration date, that brilliance isn't bound by era or tool, but by curiosity and persistence. So tell me in the comments which Bronze Age marvel stops you in your tracks. Is it the celestial clocks of Newgrange, the hydraulic alchemy of Knossos, or something else entirely? And if you're as captivated by these mysteries as I am, don't forget to subscribe. Together, we'll keep pulling at the threads of history, unraveling the untold stories of those who shaped our world long before the first history books were written. The past isn't finished speaking, are